Alright, I hope everyone's doing okay today. Does anyone have any questions over previous material, first of all? Alright. So, today we're going to start with section 8.6, and we'll see how far we can go with that. If we do manage to finish all of 8.6 and 8.8 today, which I believe is the other section we covered, I think we skipped 8.7. Yes. If we get through all of that today, then that means next time we'll review and we'll have a test on Tuesday next week, or basically Tuesday would be the middle of the testing window. Probably what I would like to do is just do one section today, section 8.6, do 8.8 on Thursday, and then review next Tuesday. It means these lectures will be a little bit shorter. I feel like we might be wasting a little bit of time like that. Unfortunately, I can't think of any way to if we can get through both sections today, we'll see if we can do that. Otherwise, it'll just be one and then a review. I'll go over the schedule once we get to the end of class rather than the beginning, so I can at least have knowledge of what we've already done today. That'll dictate largely what happens thereafter, I think. Okay, so we're going to start off with section 8.6, which is on numerical integration. And the idea of numerical integration is that there are some terms that simply cannot be integrated. There's some integrals that we simply cannot integrate by hand. And the question is, well, if we can't integrate by hand, is there a way that we can approximate it? And it turns out there's a variety of ways which we may do that. And this is the first way that which we'll examine, which is numerical integration. We'll look at an alternate possibility in chapter 9, where we can use summation. Well, a power series is what it's called. But for now, we're going to use just numerical integration. Now, there's two processes in particular I'm interested in covering here, which is one's called the Trapezoid Rule, and the other is called Simpson's Rule. Okay, so let's start off with the Trapezoid Rule. In this scenario, the first thing I want to mention is that whenever we're using numerical integration, is we're calculating the area under a curve, is basically what's happening. So when you say trapezoid rule, it's the trapezoid rule for approximating the area under a curve. Similar to, if you remember, I think in chapter 4, we talk about the Riemann sums. sort of similar to that, although this is a little more calculation based and not so much theoretical and infinite in nature. We are going to be looking at a limited number of polygons, not like a infinite number like Riemann sum basically uses. So ultimately, these types of problems where we would need to use the trapezoid rule and Simpson's rule do not really work with the approaches that we used with Riemann sums before. So, the idea with the trapezoid rule is the area under the curve is divided into in trapezoids with equal width. And so the idea is, let's look at a sketch, and I'll do just a basic example. So we have a curve, and we're looking at it from 1 to 3. Okay? So we're interested in this interval in particular. So this is f of x, and we're going to split into 4 trapezoids. Now, when we think of trapezoid, first of all, as a shape, we think of what we call a regular trapezoid, where the top and the bottom are parallel, and we have identical opposite sides that are slanted at different angles. But basically, it does have some symmetry there. In this case, we're not using what we call a regular trapezoid, because the idea is that, okay, we break this into 4 pieces, 4 trapezoids, so we have 1.5, 2, and 2.5, and then our sides are all vertical, but then we calculate our values here where this top edge may be a diagonal of some kind, or slanted line. So these 2 sides are parallel lines, and then these 2 sides are non-parallel lines, which is what makes a trapezoid. 2 opposite sides are parallel, 2 other sides are not necessarily parallel. And what's happening is that these points here, where we're making these marks now, these are the points in the curve, and we're just connecting those with straight lines. Okay? And so some of them may include area above the curve, others may include area below the curve. It just depends on how the sketch is made and the shape of the curve itself. But the idea is that we can approximate this area by adding up the area of these 4 trapezoids. Okay? So the area under the curve is equal to the sum of the areas of the trapezoids. Okay. And again, these sides are all parallel. They're all vertical lines at 1, 1.5, 2, 2.5, and 3. This side is flat, and we see that we do have an equal width of 0.5 each time. But then we have this diagonal line potentially at the top. Now this value right here is f of 1. This value is f of 1.5. f of 2, f of 2.5, and f of 3. Okay? That's basically the height of each of these, or this vertical distance at least, for each of these trapezoids. Okay? Now we think about the area of a trapezoid, because we know we have to find each of these individual areas and add them together to get the total area. Now the area of a trapezoid and again, our basic model looks like this, where we have what we call base 1, base 2, and a height h. The area is equal to base 1 plus base 2 divided by 2 times h. Okay? Now, when they are arranged vertically like this, here's base 1, here's base 2, and here's h. H is actually the width in this scenario. So what's really happening is we're taking the average of those two bases, the top and the bottom. We're taking the average width multiplied by the height. So in a way, it's length times width, or base times height, similar to what we see for a rectangle. So the idea is that a trapezoid is just a deformed rectangle. It's ultimately what's happening here with the area calculation. Okay. But this is our concept now. Our bases are each of these vertical sides on our graph, and our height is actually the width in this case. Alright, so you have f of 1, f of 1.5 with a width of 0.5, so the area of this trapezoid would be f of 1 plus f of 1.5 divided by 2 times 0.5. Now, what we're going to see happen, let me resketch the graph here that I made, more or less. 1, there's 3, 4 parts here. Connector lines. Okay. So this side is f of 1. This side's f of 1.5. This is f of 2. There's f of 2.5. And finally f of 3. So we look at the area. So here's trapezoid 1, trapezoid 2, trapezoid 3, and trapezoid 4. So we have 4 trapezoids here. So the area is equal to T1 plus T2 plus T3 plus T4. So T1 we said is the average of the two bases. Well, for T1, one side is f of 1 and the other side is f of 1.5. Divided by 2 times the width, 0.5, down here. And that's T1. T2, the bases are f of 1.5 and f of 2. Divided by 2 times 0.5. For trapezoid 3, the bases are f of 2 and f of 2.5. Times 0.5 again. And then for the fourth trapezoid, the bases are f of 2.5 and f of 3. Divided by 2 times 0.5. Now, what we can see that we have here is every single term is multiplied by 0.5. Let's say our area is equal to, we'll factor out the 0.5, and we actually have 2 on the bottom of each, so I'll call it 2 to the 4th down there, times let's see. So basically we took out the 0.5 from everything, we took out the 2 on the bottom for everything, so all we have left inside are the function values. So we have f of 1, f of 1.5 is used twice, f of 2 is used twice, f of 2.5 is used twice, that, and f of 3 is used once. Now, this is a kind of the typical formula that we see for the trapezoid rule. Okay. Now, what our goal in doing this is we're basically trying to develop the formula for the trapezoid rule. Actually, sorry, that's not to the 4th power. That's my bad. Each one of these has a 2, so it's really just 0.5 over 2 for each term. We factored it out. It's not like it goes repeated because these are being added together and they're not multiplied. So I'm sorry about that. I knew there was something off there, but I wasn't quite putting my finger on it. Yeah. So this should help us kind of identify a formula for a trapezoid rule. And the idea is that inside the parentheses, the left and right boundaries, those are used one time each, but every one in between is used twice. Okay? So whether we have 4 trapezoids or we have 40, this property should hold true. Now, out here, we always have a 2 in the denominator, and 0.5 is the width of the trapezoids. Now, we actually have a way of calculating that, so let's look at the general case. So, trapezoid rule. This is our general case. So we have the integral a to b of f of x dx, and we want to use in trapezoids. In this case, we were using n equals 4. That's how we came up with the results that we did. We had 4 trapezoids here, and we added them together. Okay. So what happens if we have n trapezoids? Well, the first thing is that the width of each trapezoid is equal to b minus a divided by n. So basically this tells us the total width b minus a is to the total width of the region that we're looking at, and we want to divide that into n trapezoids, so we take b minus a divided by n. In this example, b was 3, a was 1, and we had 4 trapezoids. So b minus a over n, in this case, is 2 divided by 4, which is 1/2 or 0.5. Okay? And we used a width of 0.5 everywhere we implemented it. Okay, so this will be part of it. And the other thing is that because each of these is divided by 2, we'll also have that width divided by 2 on the outside. So for our trapezoid rule, our area is our width, b minus a divided by n, and then we'll divide this by 2, which actually puts a 2 on the denominator, so we could think of it as b minus a over 2 times n. And we have f of x0, 2 times f of x1, 2 times f of x2. And we keep adding those together until we get to 2 times f of xn minus 1 plus f of xn close parentheses, or actually bracket, is what I use. Okay, and that's our formula for the trapezoid rule. Now, for our purposes, I'm just going to stick to n equals 4 because it's a relatively nice number to use. It's enough it's high enough to show our competency using the rule, and at the same time not being a massive obstacle from calculation standpoint. Because depending on the functions, calculations may be somewhat involved. Well, basically, these function values may be some weird decimals, is what it amounts to. So we'll just have to be careful as far as how far we round. Anyway, but this is the general pattern. We have b minus a over n represents the width. We have an extra 2 there because of the area of a trapezoid is b1 plus b2 over 2. This 2 is factored out, basically. And then each of the sides, which we'll call x0 and xn, are used once, and each of the interior pieces are used twice, as we demonstrated in our previous formula here. So this really matches up with what we see with our rule. This is b minus a over n divided by 2, which will give us the number that we need there. The left side is used once, the right side is used once, but the sides in between are used multiple times, 2 times each. And the reason for that is that, okay, this side is only part of one trapezoid, but this side here is the base on the first trapezoid and the second trapezoid, so we use f of 1.5 twice. Same thing is true of f of 2, it's part of T2 and T3. And f of 2.5 is part of T3 and T4, so we'll use that twice as well. But f of 3 is only part of T4, so we only use that right side one time. And that's why we have each of these once on the outside, but twice in the middle, because of the number of trapezoids they are part of. Okay, was a little off center there, sorry. Anyway, what may change from one problem to another is this A and B value. Move it back down a bit. These may not necessarily be 2, so if we split it into 4 parts, the nice thing about n equals 4, again, is that whatever that width turns out to be from A to B should be easily dividable into 4 pieces. Now, we don't really want a width of more than 0.5, otherwise our answers are going to be pretty inaccurate. And as you might expect, the more trapezoids that we include under this curve, the more accurate the measurements is going to be. So it'd be much more accurate if we did 20 trapezoids rather than 4, but if we're calculating this by hand, that's kind of a nightmare. And we wouldn't want to do it. Now, to an extent, we can automate this process on a computer if we want to throw it into Excel or software like MATLAB or similar. It should handle it nicely. In fact, I think the procedure is built into MATLAB and Maple and similar software. But it would be pretty easy to automate the process in software such as Excel, spreadsheet software. So if we wanted to go more than 4 or 6 trapezoids, at that point I would recommend starting to use technology as an alternative to doing it by hand. But we just want to get the fundamentals down here, and that's our purpose. And we'll just continue to use a relatively small number of trapezoids, so we can still do this by hand and in a reasonable amount of time arrive at an answer that was fairly accurate. That's the goal that we have here. So, but hopefully that will inform us as far as what the process does and how it could be extended to using more and more trapezoids to be more accurate, basically. Okay. For an example, we want to approximate the value of the integral from 0 to 1 with n equals 4 trapezoids. Now, this is an example of an integral that we cannot actually integrate by hand. E to the x squared is one of our classic examples that we like to use for that. Because for one thing, it's not something we can integrate by hand, but for another thing, it's actually an important integral in other applications. It turns out to be important in statistical applications for various reasons. Anyway, so we want to make 4 trapezoids with a equals 0 and b is equal to 1. So a equals 0, b equals 1. That means our width is b minus a over n, which is 1 minus 0 divided by 4. So it's 1/4 or 0.25. So we're going to have trapezoids. And let me just do a rough sketch of what we're looking at here. At e of 0 is 1. And e of 1 is equal to 2. It'll be a little bit lower than that. 2.7, whatever e is equal to, e to the first. 2.72, somewhere around there. And it'll be an exponential curve, so it should be a nice smooth curve. Now, this is 1, So we're going to split this up into 4 equal parts. Here, 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 and here. Okay. Draw our vertical lines. And then we can connect our points here to create the diagonals. Now, this one looks like it should be fairly accurate because the curve is pretty smooth. And we're looking at 4 pieces and just a width of 1 rather than 2. If we tried to do 4 trapezoids from 0 to 2, it would be a much different story, I believe. Because at this point, the exponential curve has not yet begun to accelerate. So it is accelerating, but it gets a lot faster, as we know, the higher we go. But then what we really need here, or what we're looking for, is the values of these marks here in between. So if this is 1 and we have 3 marks in between, these are our quarters, 0.25, 0.5, and 0.75. So we have the one halfway in between, and we split that in half again, basically. So when we say n equals 4, that means we're basically dividing this interval into 0.25 units. So that's 0.25, 0.5, 0.75, and then 1 finally. Okay. So now we're going to take that and plug it into this. So with n equals 4, we're going to start with f of 0, f of 0.25, f of 5, f of 0.75, and then f of 1. 2 times the 1's in the middle, and 1 times the 1 outside, and then we'll have b minus a over 2n on the outside of that. Okay? So our area, there's 2 ways we can think about it. We said b minus a over 2n, or we can think of it, we already calculated the width. It's just the width divided by 2, if we want to think of it that way. So 0.25 divided by 2 outside. We'll have f of 0, 2 times f of 0.25, 2 times f of 0.5, 2 times f of 0.75, and plus f of 1. Okay? Now, when we say f of 0, that means here's f of x right here. That's the function that's being integrated, e to the x squared. So we're going to plug each of these values into that e to the x squared function and calculate them. What I would recommend is going to 4 decimal places. It's usually reasonable enough that we'll be okay with our accuracy. And that's actually what I'll use on the exam whenever we get to that. So let's just go to 4 decimal places there. All right. So we know f of x is equal to e to the x squared, and so f of 0 is e to the 0, which is 1. Easy enough. F of 0.25, we'll have to go to a calculator for this one. So we have e to the 0.25 squared. You can see I get 1 point. I said 4 decimal places, so we'll go 0, 6, 4, 5. 1.0645. F of 0.5. That's e to the 0.5 squared. E parentheses 0.5 squared. So 1.2840 f of 0.75 e to the 0.75 squared (1.7551) and finally f of 1, which is e to the 1 squared, which is 2.718. Let me just double check that. 783. Yeah, I was thinking that next one rounded up. I couldn't remember though. Usually for E, I remember 2.718, and then after that, it's kind of a blur. Kind of the same way with pi with 3.14159. After that, I don't really memorize what happens, although the calculator will show you to a certain extent. So, anyway, so those are our values. So we want this once, each of these three twice, and this once. So let's see. So we had 0.5 divided by 2 times 1 plus 2 times 1.0645 plus 2 times 1.2840 plus 2 times 1.7551 plus 1 time 0.27183. Okay. Oh, sorry, this was 0.25 this time, my bad. Our width was 0.25, and then that's divided by 2, so it's 0.125 outside, and then the inside part, let me calculate that. I got 11.9215. Multiply that by 125. And so our area is approximately equal to 1.4902. Okay. So even though we couldn't actually integrate this problem, e to the x squared from 0 to 1, we could at least approximate the value of that integral. So we could also say integral 0 to 1 of e to the x squared dx is approximately equal to 1.4902. That's ultimately what we're trying to find, is an approximate value for that integral. Unfortunately, I don't have the exact value for that one. So, let's look at an example where we do know the actual value, and that way we can compare what we get. I think that'll be interesting. Let me start on a new page, though. And I think a nice trig integral would be good. let's say 0 to pi of sine x dx. Let's look at the actual value first, because we know we can integrate that. Integral of sine is negative cosine x. And so we get negative cosine of pi minus negative cosine of 0. So it's negative cosine pi plus cosine 0. Cosine of pi is negative 1. Cosine of 0 is 1, and so we end up with a value of 2. So the exact value of this integral is 2, but let's approximate using the trapezoid rule with n equals 4. And that way we'll be able to compare our answer to that with the 2 that we know is the actual value. Ideally, we probably want a little bit bigger of an interval, like maybe n equals 6 or 8. 4 at least is manageable. That's why I like to use n equals 4. From a calculation standpoint, it's not too bad. So we have f of x is sine x, a equals 0, b equals 4, or b equals pi, and n is equal to 4. So our width is pi minus 0 divided by 4, so pi over 4 is our width. So we need to start with f of 0, then we need f of pi over 4, f of pi over 2, f of 3 pi over 4, and f of 1. Okay? Or pi. Sorry. So that basically takes the pi and splits it into 4 parts, and that's our width. So you start at 0, and we count by pi over 4s basically. So pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, reducing these two, of course. Okay. So sine of 0, 0. Sine of pi over 4 is root 2 over 2. And that's 1 point, no, that's not 1 point, it's 0.707 something. Root 2 divided by 2. 0.7071. Sine of pi over 2 is exactly 1. Sine of 3 pi over 4 is square root of 2 over 2. And sine of pi is 0. Which is interesting. Our endpoints are 0. Okay. Alright, so let's see what that gives us. That means our area is equal to our width, pi over 4, divided by 2. Then inside we have 0, 2 times 0.7071, plus 2 times 1, plus 2 times 0.7071, plus 0. Could actually, well, anyway. Pi over 4 divided by 2 is pi over 8, and then inside, let's approximate this. 0.7071, technically we have it 4 times, plus another 2. So 4.8284. Multiply that by pi over 8. So we get a value for the area 1.8 0.961. Okay. Again, we know the actual value is n equals 2, or area equals 2, but you know, we came up with a pretty reasonable number for just n equals 4. We got about 1.9, so it's fairly close to the actual answer. We'd have an error of about 5% at that point, which is not terrible. Okay. Now, the book happened to do the same question, that's why I chose it, but they use n equals 8. So if we see what they did in the book here, so they have the integral 0 to pi of sine x like we used. They did n equals 4 and n equals 8. Now n equals 4, they got the same answer, 1.896, which is reassuring. And then they repeated it for n equals 8, and they actually got a better approximation. Usually what happens is when we increase the number of trapezoids, that's what we anticipate happening, and it should happen, unless this is a really weird figure. We increase the number of trapezoids, so we should increase our accuracy. We see their answer now is a lot closer to the true answer 2 than the previous one was for n equals 4. So n equals 8 gave us a much better or accurate solution. Which is, in general, if we increase n, we should get closer and closer to the real answer. That's the reality of the situation. Particularly if it's a nice smooth curve like the sine function represents. Now you can see the visualization of the intervals with n equals 4 trapezoids. You can see there's a good amount of area up here, especially on these middle two pieces. There's a good amount of area that's being left out, not to mention that we are rounding the answers. If we look at n equals 8, though, we see we see the solid lines there underneath where we have the top of the trapezoid just short of the curve in these different locations, particularly in the middle we see it easiest. Again, it's not going to be completely accurate, but we see a lot closer because those gaps now are a lot smaller with more trapezoids in there. And so it's very similar to the idea of Riemann's sum, except Riemann's sum was rectangles, not trapezoids. Anyway. Alright. Let me zoom back out now. There we go. So that's how we would complete the trapezoid rule for that problem, and I just wanted to use that one because the book also had n equals 8. That way we can compare the answer and see our conclusion based on that. Alright, so that's trapezoid rule. Let's move on to Simpson's rule. Simpson's rule is a little bit different than trapezoid rule. It actually, the purpose is the same thing, is to approximate the area, but it has a little bit of a different formula and there has one additional requirement that the trapezoid rule did not have. Now, the idea of Simpson's rule, and let me show you this in the book. page over here. Sorry. The idea of Simpson's rule and this is the explanation the book uses right here. One way to view the trapezoidal approximation of a definite integral is to say that on each subinterval we're approximating f by a first-degree polynomial, meaning that at the top of our little box we have just that one diagonal, which makes it a trapezoid. Okay. What we do different in Simpson's rule is to, instead of having just a flat diagonal, we're going to use a second-degree polynomial, basically connecting those two edges, left and right side of the trapezoid. Instead of a straight line, we'll have a quadratic curve. Okay? And so the idea is that we have our graph here, and we have A and B, and we have, let's split it up into 4 parts again, so we'll have our pieces in between. That one's not as straight as the other ones. Anyway, when we connect these together, we're going to use a parabolic curve to do it. Now, this is not necessarily a great representation of what it looks like, but I wanted to kind of exaggerate it just so you can see the difference. It won't necessarily have the same curvature that I'm displaying here, but the idea is that since this is a curved line already, if we just make this a curved line connecting these points, it should be much closer to the graph itself. Same thing here, here, and here. So the idea, and it's not nearly as drastic as what I'm showing you right, like in the middle here, especially. These are probably much closer to the actual curves once we create these. But the idea is with Simpson's rule is the top edge of this four-sided figure is now a segment of a parabola rather than a straight line. And the hope is that it better fits what's happening with the function. So Simpson's rule is especially useful for graphs that have a lot more curvature that we can help account for that with the polynomial curve rather than just a straight line that we see with a trapezoid. Without looking at the graph, there's really no way of knowing. We can maybe predict a little bit, but there's no way of knowing whether the trapezoid rule or the Simpsons rule will necessarily be more accurate than the other. It really just depends on the shape of the curve of the graph. So anyway, because there are times the trapezoid rule will be more accurate. Generally though, I think we'll expect Simpson's rule to be slightly more accurate because of the curved natures of the tops of these graphs rather than the straight line nature. Because most of the graphs that we're trying to find the area under will not have straight lines, by and large, or anything close to that. Sometimes the trapezoid rule gets closer by accident, which is always amusing, because it has excessive error above and below, and they kind of cancel out. Alright, but that's kind of the idea behind Simpson's rule. Now, the book brings up an interesting theorem, and I want us to look at this. This is theorem 8.4, which says if p of x is equal to ax squared plus bx plus c, then the integral from a to b of p of x dx, this is equal to b minus a over 6 times p of a plus 4 times p of a plus b over 2 plus p of b. Okay. Just 1 second. Ironically, I was hoping for a written proof, not a visual proof. Okay. The textbook had a QR code, and I was seeing what it linked to, and it actually has a link in there that shows the proof of this. And I was hoping it was already written out, so I wouldn't have to write it out myself. But alas, here we are. Anyway. But this is the basic approach. So if you want to look in the textbook, there is a QR code there. You can watch the video that demonstrates why this is equal to that. Unfortunately, I don't want to spend a lot of time going over that, so I imagine it might take a little while to do. This term is especially interesting looking. So, anyway. But this is kind of the principle, is that the integral of a general quadratic could be written as such, where p of x is our quadratic. So if we evaluate p of the left endpoint a, p of the midpoint, which would be a plus b divided by 2, and p of the right edge, which is b, we take the left endpoint plus the right endpoint plus 4 times the midpoint, and then multiply by the distance, or the width, divided by 6 on the outside, and that's our calculation for the area. Now we will incorporate this into Simpson's rule, the formula for Simpson's rule. That's entirely based on this concept. So now let's go ahead and look at the Simpson's rule formula. One of the things that is required in Simpson's rule is that we have an even number of polygons. And just n is even, basically. So that's the first thing. N must be even for us to apply Simpson's rule. And so the area is equal to b minus a over 3 times n times, and we get f of x0 plus 4 times f of x1. This 4 actually comes from the fact that we have a 4 here. Now what's interesting is that next we have a 2 times f of x2, that's parentheses, sorry, plus 4 times f of x3, and we keep going like that. We'll get 2 times f of xn minus 2 4 times f of xn minus 1, and then plus f of xn at the very end. So essentially the pattern that's being created here is we still use the left edge once and the right edge once, but the ones in between alternate 4, 2, 4, 2, 4, 2, 4. Okay? We start with 4 after the first one, and we end with 4 before the last one, but we alternate 4, 2, 4, 2, 4, 2 in between. Okay? And it's based on this rule right here. Now, if we have n equals 2, then our, two Simpsons rules, then our formula looks almost exactly like this. N equals 2 means we'll have 3 times 2 is 6 right here. And if we only have n equals 2, that means we have 3 terms inside of our calculation, which is the left endpoint, the right endpoint, and then the midpoint in between, which has a 4 in front of it. Once we get to n equals 4, though, it'll be 1, 4, 2, 4, and then 1. Okay? So it really just depends on how many terms we have, what exactly this is going to look like inside. Let's go back to our sin x problem that we talked about before. Notice that for sine of x with trapezoid rule we got 1.8961. Okay. Let's try the same integral with Simpson's rule. So this will be the integral 0 to pi of sine x dx. Simpson's rule with n equals 4. And again, we know the actual value is 2 in this scenario. Okay. All right. Sorry. So, splitting this up into 4 pieces, our width is still b minus a divided by n. In this case, pi minus 0 over 4, so our width is still pi over 4. So we'll have f of pi over 4, f of pi over 2, f of 3 pi over 4, and f of pi. Okay? And we actually calculated all this before. I'm looking at the other sheet now. So let me fill in these values real quick. It's really, I just couldn't remember that last number again. So we have these 5 values. Zeros on the endpoints, and then we have some values in between. Now, for Simpson's rule, the area is the width, which is pi over 4, divided by 3. It's width divided by 3, if we look at the formula. Because it was b minus a over 3n. b minus a divided by n is the width, and the other 3 is what we also divide by from there. So if we want to think of it as the width over 3, that's one interpretation. So f of 0, 4 times f of pi over 4, 2 times f of pi over 2, 4 times f of pi over 4, 3 pi over 4. Sorry. Actually, the value is the same. And then f of pi. Okay. Sorry about that. So again, the pattern is 1, 4, 2, 4, 1. And again, we have this alternating pattern starting with 4 and ending with 4, and then alternating with 2's in between. So if we had 6 terms, it would be 1, 4, 2, 4, 2, 4, 1. Okay. And so now we go through and we do our calculation. On the outside, pi over 4 divided by 3 is pi divided by 12. It's 4 times 3, just multiply that together. And then inside, f of 0 is 0. 4 times 0.7071. 2 times 1 plus 4 times 0.7071 plus 0. I'm pretty consistent with that, apparently. So it's pi over 12, and then what do we have inside there? With 7.6568. And when we multiply that by pi over 12, we get 2.0045. So what ended up happening here is that we slightly overestimated the area where the trapezoid rule was a little bit below. And again, we can't really tell necessarily just by looking at the graph which way it's going to go. This one is a lot closer. Simpson's rule is. It is a lot closer to the value. So we found with the trapezoid rule, we were off by about 0.1. Here we're off by about 0.005. A little bit less than that, actually. So it's a lot closer in that regard, and we kind of expect it to be because the sine function in this case is a very nice curve. It doesn't have a lot of curvature near 0, but everywhere after that it basically does, which is very nicely lends itself to that parabolic segment shape that we're creating with Simpson's rule. Okay. I want to do one more problem with this. Okay, let's look at an example. What can we do? What can we do? Let's do the integral from 1 to 2 of 1 over x squared dx. Now, the actual value here, let me calculate that real quick. We know the integral of 1 over x squared is negative 1 over x. It's just a power rule integration. So it's not like we really need to use any kind of approximation methods for this integral. We're just trying to compare the two methods in this example. So it's negative 1 over x. If we plug in 2, it's negative 1/2 and then plus 1. So the actual value should be exactly 1/2. Okay. So we'll have that. But approximate the area. Using n equals 4 for both the Trapezoid Rule and Simpson's Rule. Okay. Now my recommendation here is, before we calculate the actual value of the Trapezoidal Rule and the Simpsons Rule, let's get the function values first. Which is f of the function values in this function at 1 over x squared. First of all, we calculate the width, which is the same in both rules. Width is b minus a divided by n. In this case, it's 2 minus 1 divided by 4, which is just 1/4 or 0.25. Now the difference in this case is that our first value is 1, so we'll start with f of 1, and then we'll count up by 0.25s there from there until we get to 2. So f of 1.25, f of 1.5, f of 1.75, and f of 2. Okay. Now we plug in x equals 1 to 1 over x squared, so 1 over 1 squared is just 1. Then we'll have to calculate the rest. 1 divided by 1.25 squared is 0.64. 1 divided by 1.5 squared. This is a 0.4 repeating, so we'll just go to 4 decimal places. 1 divided by 1.75 squared is 0.3265. And then 1 divided by 2 squared is 1 over 4, or 0.25. So that gives us our function values first. Because we know we're going to use those 5 numbers in both the Trapezoid Rule and Simpson's Rule, I think it makes sense to go ahead and find them to begin with. Now we can just calculate each one individually. So let's look at trapezoid first. Call it T4 since there's 4 trapezoids. So we take our width divided by 2 on the outside, and we'll take f of 1 plus 2 times f of 1.25 plus 2 times f of 1.5 plus 2 times f of 1.75 plus f of 2. So again, trapezoid rule, we multiply each of the terms in the middle by 2 and the beginning and end by 1. So this would be 0.125, and then we get 1 plus 2 times 0.64 plus 2 times 0.4444 plus 2 times 0.3265 plus 0.25. Alright, so let's calculate that out. And that works out to be about 0.5090 if we go to 4 decimal places. We do see that, and we know the actual value is 0.5, so it's actually not that far off. But I wonder if the Simpsons rule gives us a closer number. So look at Simpsons next. Now Simpsons, call this S4, will be our width, 0.25, divided by 3. And we'll have f of 1, 4 times f of 1.25, 2 times f of 1.5, 4 times f of 1.75, and f of 2. Now, 0.25 divided by 3 doesn't come out to be an exact number, so I'll leave that alone until the final calculation. And then fill in the rest, so we have 1 plus 4 times 0.64 plus 2 times 0.4444 plus 4 times 0.3265 plus 0.25. And we can approximate from there. 1 plus 4 times 0.64 plus 2 times 0.4444. There will be a little bit of rounding error as we see. Plus 4 times 0.3265, and then plus 0.25, and then we multiply that by 0.25 and then divide by 3. So we get a value of 0.5004. All right. So, ultimately we got pretty close with both of these approaches, the Trapezoid Rule and the Simpsons Rule. We see that Simpsons did get a little bit closer because we know the actual value is 0.5 in this case. Simpsons got a lot closer actually. Generally, the way that we say this is that the Trapezoid Rule is accurate to basically 2 decimal places, while Simpson's Rule is accurate to 3 decimal places. So 1 additional place of accuracy is essentially 10 times better in this scenario. But again, we can't necessarily predict how that's going to happen. We normally expect Simpsons to be a little bit better than Trapezoid, but sometimes Trapezoid Rule gets lucky with the way that the divisions work out and the calculations go. On your exam, and I'll talk about this a little bit more when we review, but on your exam you can expect a similar problem to this, where I have you find the Trapezoid Rule and the Simpsons Rule for the same integral, for the same definite integral with n equals 4, as we demonstrated here, and I'll give you an actual value that you can compare your answers to. I think it's nice to have that actual value because, 1, we can see how close they are to the actual answer, and 2, it also tells us if we've done it correctly, because we should expect to be fairly close to that actual answer. It won't exactly be equal, but we'll know if we're way off from the answer. So it's kind of a nice way to check our work, I think, so that'll be good as well. But yeah, this is how I would recommend you work that problem as well. We calculate our width, figure out our function values, and then plug everything in into the trapezoid and then Simpsons, and we can compare from there. Does anyone have any questions on that? Now, some books also teach what's called the midpoint rule. I don't see it in this one, which is fine. I don't really worry about it too much anyway. The midpoint rule is basically a rectangle where the midpoint is the function value. It's a little bit different calculation. It has, again, pros and cons. I think these two are more interesting, though, and generally more accurate as well. Which is probably why the third one isn't mentioned here in this section. Anyway, let's see. Let me go ahead and just give you homework, I think. Because we're already at about an hour and a half. I don't really want to dive into anything else right now. On page 564, look at number 15 and 23. And if you look in the textbook, I'll show you my page real quick. Zooming in. Okay. In these problems, they want us to use the Trapezoid Rule and Simpson's Rule with n equals 4, which is nice. Maybe that's not the two problems I want to use. I think it'll be alright. Famous last words. This is just for practice, but I do hope you at least try one of these, if not both. The calculations are going to be a little bit more involved because of the expressions they're giving us here. Square root of 1 plus x cubed, and then x tangent x. I know the square root of 1 plus x cubed may not be integrable. It may be or may not be. I doubt x times tangent x is, although it might be possible with integration by parts. So unfortunately, I don't think we have exact values to compare those two, but you should get your numbers pretty close together for both the Simpsons and the Trapezoid Rule, as we've been seeing in our problems that we've been working today. You know, they're not far off from each other, and they're not far off from the actual value in most cases. Even at n equals 4, that's pretty impressive, I think. Anyway, let me zoom back out. So we'll leave it at that. So go ahead and try those out. And next time we will cover section 5.8. That's Thursday. And then next week we'll review on Tuesday, and then after that I'll open up testing for test 2 from basically Tuesday night till the following Monday night. Okay, and it'll be this test for chapter 8 will be basically all one piece, all one test. It won't be in 2 parts this time. So it'll be a little bit more conventional. Like the first part of the last test, you'll have to upload your work for each part. One page at a time, basically. And then I'll go back in and grade it afterwards. I still haven't graded part 2 of your last test, but I'm going to do that right now, and so I should finish that by later this afternoon. So I don't want us going into the next test with the previous one not finished grading. That's just silly. So anyway, so I'll get to work on that. Y'all can work on this, and y'all have a good day, and we'll do this again Thursday. Take care of yourselves. Bye.